Right, we've been discussing about deadlocks. We looked at what is a deadlock, what are the necessary conditions for a deadlock. We looked at different techniques through which you could prevent a deadlock. We also looked at deadlock recovery. Now, deadlock avoidance and deadlock detection are the next concepts we're going to be diving into. In this segment and the next, we will talk about deadlock detection. So there are four main constructs we've been dealing with: deadlock prevention, avoidance, detection and recovery. So if you look at prevention and avoidance, they are precautionary measures, something which you take up to try to make sure that the deadlock does not happen in the first place. But for some reason, if you're not able to take up such measures, then it is possible that a deadlock happens, in which case you need to first be able to detect one when it occurs, and then you will go ahead with the recovery measures which we've already discussed. So in this segment and the following segment, we're going to look at deadlock detection. So when we discussed this concept called resource allocation graph, I spent some time talking about specific cases where it is possible simply by looking at the graph to identify that there is a deadlock. Specifically, when we have only one instance of each resource type, I mentioned, if you remember, that if your resource allocation graph has a cycle, it implies that there is a deadlock. There is no second thought required. So formally, that is the case we're going to be looking at right now. So if you have a single instance of each resource type, we do something called converting the resource allocation graph to the wait for graph. WFG is nothing but wait for graph. So, and that helps us to detect the presence of a deadlock. Now, you actually don't need to do this step per se, because as I said, if you have your RAG and if you know for a fact that there is only one instance of each resource type, all you need to do is check for the existence of a cycle in your RAG, and that itself will tell you that there is a deadlock. So you don't really have to convert it to a wait for graph in that sense. But the thing is, this is a very simple toy example. You have only two processes and two resources. It's a very small RAG. Just by looking at the graph, you can spot a cycle. But in a computer, that's not going to be the case, right? We're going to have multiple processes, probably tens or hundreds of processes running at the same time, hundreds of resources. The interdependencies and the connections in the graph are going to be very complex. So simply by looking at the graph, you might not be able to spot the presence of a cycle. So in such cases, converting the RAG to the WFG makes things easier. Why so? What exactly is this WFG and how do you get that from the RAG? So WFG stands for wait for graph, and how you obtain it is you simply remove all the resource nodes from the RAG and you extend the connections between the process nodes themselves. So converting a RAG to a WFG, remove all resources and simply connect the corresponding process nodes with edges. So if you look at this resource allocation graph on the left side, if you are familiar with the last few topics we discussed, you will know this is the example we've been working with for quite a while now. Two processes, two resources, one instance each, classic deadlock case. Now you take this RAG, you will remove this resource node, and this arrow from P0 goes and directly connects to P1. Similarly, you will remove this resource S. This arrow this edge from P1 connects to P0. That is exactly how you get a wait for graph. So what is this graph trying to represent? What is the physical interpretation of this graph? It tells you which processes are dependent on which other processes. So if you remember, when we discussed RAG, we saw something called a request edge and something called an allocation edge, right? So P0 is requesting for Q, but Q has been allocated to P1. So only when P1 lets go of Q, this Q can be given to P0. So in that sense, P0 is dependent on P1 for some resource Q. Similarly, P1 is dependent on P0 for some resource S. That is exactly what we're depicting in the wait for graph. P0 is dependent on P1 and P1 is dependent on P0. We don't care about which resource this dependency is about, right? It could be Q, it could be S, it could be R, it could be any resource for that matter. When we're talking about deadlocks, what we care about is which processes are dependent on which other processes. So that is why we remove all the resource nodes and keep only the process nodes in the wait for graph. Also, you can see it simplifies things. So you had 4 nodes and 4 edges. Here it came down to 2 nodes and 2 edges. So the size of your graph, both in terms of nodes as well as edges, is significantly coming down. It's going to be easier for your system to detect cycles and so on and so forth. So that is the reason we first convert the resource allocation graph to a wait for graph. Once that is done, what do we do? Simple. You check if the wait for graph has a cycle. If yes, deadlock. If not, no deadlock. So quick recap, there's nothing much to talk about here really. You want to your aim is to detect a deadlock, assuming there is this confirmation or this assurance that for every type of resource you have only one instance. You take the RAG, remove all the resource nodes, extend or combine the request and allocation nodes and edges into one edge, thereby creating the wait for graph. Check for a cycle in the wait for graph. If there is a cycle, it's a deadlock. If there is no cycle, there is no deadlock. As simple as that. So that is the end of the concept per se. I would like to conclude this segment by leaving a question for you to think about. How do you look for cycles in a graph? So and by how do you look for cycles, I don't mean in the manual sense. Like if I give you this graph, you can take a pencil and paper and trace it out and tell me this is a cycle or this is a cycle. But what algorithm can you ask a computer to use to look for cycles in a graph? So that is more into data structures territory, so I'm not going to discuss the answer to that, but it is an interesting question, so I would like to leave it over there. And with that, we conclude this segment on deadlock detection for single instance of each resource type. Thank you.